And increase size of that. Let me see this. Okay, so this is converting all the. Boy, my eyes are bad. I thought that was a minus. So it's converting all the numbers from 32 to 212 in Fahrenheit to Celsius, and then it's converting all the Celsius from 0 to 100 to Fahrenheit. Okay, I know where I'm headed. Let's see. 32. 212. Okay, so loop's working right. 0 to 100. Okay, so that loop's working right. It's kind of a bizarre result. Typically, what that NaN means, in case you're curious, not a number. Okay. Double Celsius, double Fahrenheit, double. Okay. Bring in F, but you're not using F here. So your parameter, I'm guessing, I don't remember the formula, but that should be an F there. Now, sometimes this causes you a problem since this is both integers. Sometimes it does integer division. That's another possible problem. You can easily get around that by putting a 0.0 on there, and that'll force it to make these doubles. Down here, I'm bringing in the parameter C, so I think I want that to be a C. Same issue here. I'm not sure about that, so I'm going to throw a .0 on one of them. Make sure it's right one. Return FR, return CE. Okay, calculating C and F. I have no memory, but I think that's the one for double. FC and then C. Okay, let's see what that does. 0 degrees Celsius is 32 degrees Fahrenheit. 32 degrees Fahrenheit is 0 degrees Celsius. Okay, I'm assuming all the other numbers are correct, but that's what was wrong. Let's continue on in this chapter. This is chapter 6. Yeah, chapter 6. And working with arrays. And this talks about searching arrays. And we're talking about using the binary search. And just for fun, I'm not going to look at the code on that. I don't always get this right the first time. Sometimes I even have to look at that sheet. Look at the general algorithm. But I want to declare my arrays. I want to give me a good example, so I'll mix it up with C#. And I'm just not having much luck here. There, finally. Okay. So I'm going to have Get rid of those. Get rid of those. Now down here, I'm going to have my my array. And syntax all messed up. int, and then the variable name. Nums 10. Or let me do it this way. 1, 8, 15, 23, 50, 72, 81, 103, 107. My search value, I'm going to say, is 103. Now, I know the general idea. We talked about that last time, where you split your numbers in half, and then you're searching that value in the middle. So I'm going to have I think a Boolean flag, done. Now set equal to false. And while I'll say done is equal to false, or you could say not done. When I say not done, you have to put an exclamation in front of this, like that. I don't know, I think I like the other way. Okay, well, done is equal to false. Now I'm going to have to refer to my length of my array, and I may have to cheat after all to find the length. Maybe I'll hard code it. Not the best way to do it. We'll take a look at the right way here in a minute. 3, 6, 9. Okay, so my length is 9. Now I want to divide 9 in half. And so I'm going to say, the index is equal to, I'm going to say, initially I said my index up here equal to length. I'm actually just wondering if I can wing it and write the code for the binary search. So that's what I'm doing. I'm going to take my index, I'm going to divide it in half. I don't know what that's going to do exactly.
I thought C doesn't have false or true or false. It's 0 or 1.
You're right. Isn't there a Boolean? I'm thinking of a different language, aren't I? I'll run it here in a second and check it. It didn't give me a little red, but then again, I haven't tried to compile it yet. See, it makes me think there is one, but the fact it's popping up with all that doesn't necessarily mean anything. Okay, so let's run this. All right. I am mixing up languages. Okay, well, I'll use this. I use done. 0 means it's still got more to do. There we go. Now I'm going to print out this result. D/in index. Four. Okay, that'll work. Now, we're going to need to have a smallest value, like your min, and that's initially going to be 0, because our first entry in our array is 0. And I'm going to have a max, which is equal to 8. So instead of hard coding this like I just did, I'm going to take 8 minus 0 divided by 2. So I'm going to have my max minus my min. Okay, so I don't think I'm going to use length. Okay, so 8 minus 0 is 8, divided by 2 is 4. And then I want to check to see if that's my answer. So if nums of index is equal to my search value, then I'm done. So I want to do a printf, found it. I'm going to do a printf actually printing out the value just to verify. Nums index is working. And then I want to set done equals to 1. Okay. Now, if it's equal, that means I found it. Else, if nums index is less than search value, so the number I found is less than the number I'm looking for. I'll have to think about this one. As soon as I remember the there. Okay. So if my number of my index is like 50 and my search value is 103, that means I'm low. So num index is low. And I probably won't get this right the first time, but my min is then going to equal to my index, and my max doesn't change. Else, there's only one other possibility. If it's not equal to, it's not less than, must be greater than, then my max is going to equal to my index. And obviously I don't want that there. Okay, so comes through here. If I guess if it's exactly the number in the middle, fantastic. Means I found it. Set my flag to 1, print out the result, and I'm all done. If it's not, then I check to see if it's less than or if it's greater than. And based upon I adjust either min or max. And then that affects my next index. Yeah, it should work. Famous last words. Yeah, worked real good. Okay. What have I done wrong? Let's see. Else if num index is less than search value. Okay, I did view logs. Num undeclared. Oh. Nums. That's not a good sign. It's running forever. Well, let's each time through print our min and max. %d and %min equals %d and max equals %d / n min max. Okay, 0, 1, 2, 0, 1, 2, 3, 4. 50 is the first one. Okay. Where's the debug at? There. I do a debug. What if I have to set it or not? Attach to process, debugging window. Let's try that. Yeah. Choose that. Nah, still not kicking out. Well, there's more than one way about that. In int next num. I'm gonna do my scanf %d and next num. Initially, min is 0, max is 8, so that's good. Now I'm gonna type a number in and press enter. Min is 4, max is 8. Okay, because my value is low, so that's good. Next time through, it should do 8 minus 4, which is 4 divided by 2. I see it. Plus. Okay. 0 plus 8 is 8. Divided by 2 is 4. So then I got 4. 4 plus 8 would give me 12. Divided by 2 would give me 6. So I'm still low, I think. So 6 plus 8 is 14. Divided by 2 gives me 7. Found it, 103. Is that the one I was looking for? Yep, I was looking for 103. So what does the principle behind this is you start out with your smallest value and your largest value. And you take the position of it. This is position 0. This is position 8. So that's position 0, 1, 2, 3, 4, 5, 6, 7, and 8. So first time through, it's calculating index. So it's adding your min plus your max. Order doesn't matter, just seemed wrong. Okay, so our min is our first value here, which is 0. Our max is 8. So pass 1, min equals 0, max is equal to 8. Then it calculates index. 0 plus 8 is 8 divided by 2. My index is going to be 4. I look in the fourth entry. And this is my fourth entry here, and I see if it matches my number. That's why I'm doing the equals here. It doesn't because my number is 103. This is actually low. So it's checking if it just seems like a backwards day for me. Again, not that it matters. So if my search value is greater than where I'm at is my current index is 50. And the search value is greater than that. Well, my search value is 103, so it is greater. It's over on this side. So I readjust it, and I put my min equal to the 4. So I'll come down here, and I said my min is equal to 4. My max doesn't change. It's still 8. So now I want to do my index. 4 plus 8 is 12. 12 divided by 2 is 6. So now I'm looking at this one right here. And I'm going through, it's not equal. And my search value, which is 103, is greater than 81, which means that this is true. So I have to reset my min. What's my min? 4 plus 8 is 12, divided by 2 is 6, so my min would now be 6. My max would be 8. 6 plus 8 is 14, divided by 2 gives me 7. So the next time through, I'm checking it against the 7th entry, which is 103, which matches. Now, one thing has to be true on this, it has to be sorted. This does not work if it's not sorted already. You could do a bubble sort or whatever to do that, but it has to be sorted. And I'm not sure if I got this right or not. And the reason why I'm not sure is because everything came up nice with no decimals. So let me add another number on here, 110. And my search value, let's say I'm looking for 1. Now, besides found it and besides my answer, maybe I want to actually print the index too, just to make sure that it's working. Okay, so if I run that, I need to get rid of that scan. When I put this scan F here, that's like a pause. And I don't want that there anymore. Okay, now I'm searching for 1. Found it at index 0. That's promising. Let's see if I have decimals. I still have my length hard-coded. Let's try that again. And I'm not using length, I don't think, at all, so I'm going to get rid of that. Well, maybe I am using it. Index equal to length. I can recalculate the index down here, so I shouldn't need to calculate it all here. Just define it. Okay, that looks better. Okay, so I'm doing my min plus max. 0 plus 9 is 9. Divided by 2, I don't know what it is. So let's see what that gives us. I don't know if it rounds, if it truncates, but we'll see. Okay, so 0 plus 9 is 9, divided by 2 is 4.5. Obviously didn't round, it truncated. That's fine, maybe. So it's less than the number at the fourth position, which is 50. And so then what it adjusted is adjusted to max. It set the max equal to 4. Then it takes 0 plus 4, which is 4 divided by 2 is 2. Comes down here to index of 2, which is 15. Still not right. It's lower than that. So readjust max. 0 plus 2 is 2. 2 divided by 2 is 1, which is this position. Then I do 0 plus 1 is 1. Divided by 2 is 0.5, but then it goes to 0. I don't know if I feel good about that. Let's try search value of 110. It's all since infinite loop. So maybe I need to do is to round it instead of truncating it, because I think it's just truncating off the decimals, not rounding at all. It'll always be 1 decimal place. It'll never be more than that. So I can bring in math. Oh, I already got math there. And down here, when I do this calculation, I'm going to take that result. I'm going to multiply it times 10. That'll move it 1 decimal place. And then I'll do a round. Hopefully I'm remembering that command correctly. Then divide by 10. Maybe. Obviously not. Okay, well, let's take I won't waste your time on that. Let's go look at the code and see what I've done wrong. Arrays, search and arrays. Okay. It's linear search. That's just going through it. That's boring. That's just going through it from your start to your finish, 0, and then you're seeing which one matches. Here's an exciting one, the binary search. One thing note here, array of 1 billion elements takes a maximum of only 30 comparisons to find the search key. Unreal, the efficiency that goes along with this. Compared to if I had 1 billion entries in my array, I'd have to search linear. Potentially, my worst case, if my number's at the very bottom, I'd have to do 1 billion comparisons. Compare it against first one, compare it against second one, compare it against third one. Where this is just 30 comparisons. And again, the reason why is because it halves the elements each time. And this is based upon a principle that you may have heard in a little riddle. It's like in probably one of those the story they told you way back when about somebody who talked with the king, and the king wanted to give him a bunch of money and said, no, that's fine. Just take 1 penny, take a checkerboard, chessboard, put 1 penny in the first spot, and then just keep doubling it for all your spaces there. And that's how much money I want. And when you start doubling something, it very quickly, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, I don't know, let's say 9,000, 8,000, 16,000, 32,000, 64,000, 128,000, 256,000. And you see it's increasing, 512,000, 1 million, something. I think that, but I don't know. Now there's 64 checkerboard, chessboard is 8x8, so 64 of them. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. We're not even halfway through a checkerboard. We're about a third of the way. And look how large it's become. The binary search goes in reverse. It takes this number of entries and cuts it in half and goes to here, which cuts it in half and goes here. So it's still the same escalation going the other direction. Okay. Here's where it's talking about low and high. That's always the algorithm for it, is you work with the low and high. I call mine min and max. Okay, binary search of a sorted array. Okay, looks like they have it in a separate function. Okay, they don't use a flag, they use low and high. Why, low is less than or equal to high? Oh, because it could not find, there's a possibility it can't find it. Here's where you take your middle, exactly middle value. You take your low plus your high, divide by 2. That's what I had in my failed code before I started changing it. I had my min plus my max, divide by 2. That gives you your middle value. Display subarray using this loop iteration. I think what they're demonstrating there is you just cut the array in half. If search key matches the middle element, return a middle. Because this means you found it. And that's what I had here with the equals. That means you found it. Else, if search key is less than the middle, which would be this one. I'm going to go ahead and put it here just so I can wrap my mind around it, what I did wrong. Okay, so if search key is less than your middle, then high is equal to middle minus 1. High is equal to index minus 1. Let's try it now. I'm searching for 110 right there. Nah, I still have an issue. Let's see. Okay, middle minus 1. Search the low end of the array. Else, low is equal to middle plus 1. There it goes. So that's what I had wrong there. I didn't have the plus 1 and the minus 1 out of the algorithm. This is just like a general introduction if you're going into computer science and you have to take that data structures class. Let's say you go into some pretty heavy algorithms. This one's just kind of fun. It's like where you have your low here, your high here, you find your exact middle. If the value you're searching for is less than or greater than, then you adjust either the min or max, not both of them. Is there any questions on that code? What you usually have is you don't have the code already given to you, though you can Google it and find it pretty easy, so it's not hard to do that. The idea is you go into Wichita State and you're taking that data structures class and you're trying to understand how to set up all those. It gets you thinking how to program arrays. And so when you got something more complex than what you can just find in any Google search, then it helps you figure out what you need to do. Usually, what I'm looking for when I can't figure out how to do something new is I come here and maybe I do C programming, binary search, and I look for some kind of algorithm, sometimes pseudocode. Binary search program. Unfortunately, probably so many just give us the code. Yeah, there's no algorithm here. What pseudocode? Another class you'll see that called is a class called algorithms. Pseudocode is like fake code to try to get you to wrap your mind around it. Geek for geeks. And yet again, they just give us the code. Oh well. Pseudocode is where they kind of give you the general idea what to do in words. So if you're trying to figure out, like in my case, it'd be words would be find a middle index. Take your low plus your high, divide by low plus high, divide by 2, and then compare your search value to the array entry at that middle index. And I'm being way too wordy there. Pseudocode is not wordy, as you can see from these examples. From a pseudocode, you should be able to then write your code. You see it says initial passes to 0. So that said like a variable called int passes to 0. Failures to 0. Int failures equals 0. Students. Int student is equal to 1. While student counter. So while the variable student is less than or equal to 10, and then beginning curly bracket, closing curly bracket, input the next exam result. That's probably a scanf. If the student passed, so passed. So I might check if the exam score that they just entered is greater than what's passing? Greater than or equal to 70. D is considered passing in some cases. Then you'd increase passes by 1. So passes equal passes plus 1 or passes plus plus. Else, failures equals failures plus 1 or failures plus plus. So that's the idea. If you got a good pseudocode, you can just write your code directly from it. Now let me try to find an algorithm example so you see the difference in them. Algorithm follows a more rigid approach. 50 examples. Bake a cake. I don't want to bake a cake. Algorithm and programming. 3 essential algorithm examples. Code Mentor. IO. I wonder what IO is. Virus. Let's go here. I don't want to spend a weekend rebuilding this computer. Okay, algorithm add two numbers. Check prime number, find a factorial, find all the roots of a. Ooh, that's a good one. Maybe. These are not really formalized algorithms. This one might be, kind of. That's almost getting into pseudocode. Numerical methods, algorithms. In programming books, what they usually give you, I suppose they give you pseudocode, but a lot of times they give you algorithms, and you have to program it. Oh, this is the entire book. May not find my algorithms. Gram-Schmidt optimization. $607. Oh, that's ridiculous. Algorithm in figure 1.2. This, I think, is what they're referring to. This is what they use as algorithm here. And it's a very concise. They use precise definitions, what this all entails. Like here, to multiply. I is, I'm assuming, our rows, which goes from 1 to m. J is our columns, which goes from 1 to n. And we're taking the little a is the individual elements in a matrix, if you've had college algebra. And multiplying it times x. Now, x, I don't know what it is. Then I'm adding it to b, specifically bi. I don't know. I'd have to look at the... Unfortunately, what you'll find, and this is more if you're going in mathematics, is they give you nice algorithms and so forth, but they don't give you one example. And you're sitting there, what in the world is this doing? This finds a residual norm, and it's been a long time since I've had calculus, so I don't even remember what that is. But that gives you the result. But anyway, that's an algorithm anyway. That was a fun class. I like that class. That was it's called numerical calculus, but it's called numerical methods. And if you're taking calculus, all the different calculus functions you can do on the calculator, the intersect method, that is using calculus. It's I think a method from Calc 1 or Calc 2. And it's how to program it in your calculator. It's how to program it in C, C++, or whatever. Anyway, there's talk about binary search. Okay, multidimensional arrays. You can have multidimensionals like a matrix. So in college algebra, you had matrices. Maybe it'd have a 2 by 2, 1, 2, 3, 4. And then you would add that to another matrix. Maybe -7, 5, 1, and 6. If you haven't had college algebra yet, the idea behind this is you add together the corresponding entries. So I'd add together this 1 and this -7, which gives us -6. I'd add this 2 and 5, which gives us 7. I'd add 3 plus 1, which gives us 4. And I'd add 4 plus 6, which gives us 10. And we'll actually program this after I see the syntax, because I have to refresh my memory on multidimensional arrays. Different languages handle it differently. But that's where we're headed. It's called a double scripted array. Some of them will do two brackets, a pair of brackets here, a pair of brackets next to it. Some will do variations of that, language-wise. Now, you always want to consider it. Your first entry here is your row. Second one is your column. I don't know why, but it's always row by column. Here's how we refer to it. In this case, it's the two brackets next to each other, where I is your row and J is your column. Okay, here's how we declare it. So let's go do this. This is what I'm going to work with. And let me clean all this out. int a 2 by 2 matrix equals, and 1, 2, but what's the syntax on it? Braces inside the braces. Okay. 1, 2, comma, and 3, 4. Closing brace, semicolon, and then B, this, and my B was -7, 5, and 1, 6. I'm trying to remember how to define something here. Define rows equals 2. I think that's how I do it. Define columns equals 2. So down here, instead of hard coding this, you can put rows and columns. Rows and columns. Now keep in mind, it starts at 0. So when I search through it, I'm going to have row 0. That's going to be like the 1 and 2 in my first matrix. And I'm going to have row 1, which is going to be my 3 and 4. So when I set up my for loop to multiply these together, actually I guess I need another one. int c rows, columns, and I think I can do this. We'll see. See if it gives us an error. Doesn't like my define. lowercase. No, I got a lowercase. Rows and then value. Okay, so I don't want the equals. Okay, doesn't like something else. Probably doesn't like this. Okay, instead of sitting there guessing, it's not going to make our program run any slower. Semicolon. Okay, so my errors are all gone on that. Question becomes if I even needed the zeros, but I got them in there. I'll leave them in there. Now I want to loop through. So I'm going to say for int, and I could say lowercase r for everything lowercase for just a variable called rows equals, starts at 0. And I want to continue while my rows is less than, and then I'll make it uppercase rows. Rows plus plus. Not sure if that's the exact best way to use variables, but we'll go with that. And for int, columns, all lowercase, starting at 0. Continuing while columns is less than columns, my definition up above. Columns plus plus. Oops, no semicolon there. That'd be a bad mistake. Then I'm going to say C, rows, columns, is equal to A, rows, no, I want this, columns, plus B, rows, columns. Okay, so now we want to print it out then, see what it looks like. So printf, percent bracket, %d, %d, bracket, /n. Then I'm going to pass C, zero, zero. Row 0, column 1. Then my next one, C, row 0. I meant that the first one's row 0, column 0. This is row 0, column 1. And then printf, bracket, %d, %d, bracket, /n. And this is row 1. Remember, it starts at row 0. This is row 1, column 0. This will be 1, 1. Okay, let's run that. And -6, -6, -6, 7, 410, 410. So we just wrote a program to add two matrices together. Now you don't have to hard code them like you'd see me do there. You could ask the individual for the numbers. Now I did a simple one because I didn't want to think too hard tonight. But there are more challenging ones than this. You may have seen this in college algebra. You may not have taken college algebra yet. What am I in here for? Get out of Paint.net. Paint.net just does not work well with my tablet, I finally discovered, and I have to use this new photo, which I don't know quite yet. Paint 3D. Tablet works fantastic in this. There's no lag or anything. So I got 1, 2. It is a little slow though, but it doesn't cut out on me. This, and here I'm multiplying two together. So I'm multiplying this matrix times this matrix. Now how you do it is you take this row times this column. So you take 1 times 5 plus 2 times 7. And then this next one, you take this row times this column. So you got 1 times 6 plus 2 times 8. Then you take this row here times this column. So you take 3 times 5 plus 4 times 7. And then you take this row times this column. 3 times 6 plus 4 times 8. And this always throws me. I have to really think hard on it. I'm taking row 0 here times column 1. This is of my first matrix, like A. Times column 1, column 0. That's column 0 of B. Then this one is row 0 of A times column 1 of B. Then down here, this will be row 1 of A times, let's see, row 1 times column 0 of B. And then this will be row 1 of A times column 1 of B. Now what you have to look for on this is you have to look for patterns. You see how this is row 0, and then goes row 1 to row 1. Probably, then I can go with my loop from row 0 to row 1. Let's try it. I'm just curious. 5, 6, 7, 8. Let me change these. Okay, so my rows is going from 0 to 1, so that's good. That's already set up. Okay, so that's changing. And then coming from over here to over here, my column is going from 0 to 1. That's set up. And here's probably the hard part. Okay, at this point, I have to think this through. Pass 1. Pass 1. My rows is 0. My columns is 0. So 0, 0. If this is C, 1 times 5 is 5. 2 plus 7 is 14. That's 19. 1 times 6 is 6. 2 times 8 is 16. 16 plus 6 is 22. That's 15 and 28. Show you how bad I am at math. 18 plus 32. 50. Okay, I think that's what my answer should be. Now, 0, 0 would be this right here. That's my referencing. Row 0, column 0. This one, except for it's harder when I'm thinking now. Because this is row 0, column 0. This is row 0, column 1. Row 0. That's changing. I'm not going to be able to think of that tonight. That's sad. I should have stuck with a simple example, the adding. Let's say they do multiplication. Okay, so they set those. Maybe they don't even do matrices. They initialize it. Again, you can put in a for loop. You can ask in a for loop. You can ask for a scanf if you want. That kind of goes over what we've just been talking about, columns and so forth. Here's our rows and columns. Probably didn't look a whole lot different than what we did. They're just doing grades. That's boring. Okay, let me cheat. Go to my best friend. Let's see, C programming, multiplying matrices. Okay, so I'm looping through there. That's nothing. I think that's just printing off the matrices. Okay, loop 0 to that, there, and then I need another one. CDK. C D then K. K is equal to 0. Continue while K is less than. Columns and rows are both the same, so I shouldn't have to change anything there. K plus plus. So then, sum. That's it. Sum is equal to sum plus A CK times B KC, KD. This is going to be right down here. And let me double check that. That's going to be within all those that have braces on. Okay, so I got all those now. And then brace there, and then after that first brace, I need to have that. That's going to equal to my sum. Then I set sum equal to 0. Let's see if I'm even close. Not even close. Rows and columns. No. What do I want? CD. That doesn't look good. $22, $43, $50. My first one is messed up. One, two, three, 4, 5, 6, 7, 8. Did I do my math right by hand? 1 times 5, 2 times 7, 5, 19. That looks right. All these start at 0. All of them increase by 1. CK, CK, KD, there it goes. I hadn't initialized my 0. I hate when programming languages don't notify you that. So it's always a good idea, programming wise, to set it equal to 0. Now you see I had to cheat. I knew generally what to do, but it's hard to wrap your mind around some of the algorithms. And if you go out there, assuming I could go to the right site, you'd find the algorithm instead of the actual code. Okay, so what it's doing is I'm looping through 3 because I'm going. The rows are changing, the columns are changing, but then within there, this one is let me think. This is row 0, And the 5 would be column 0. This one is row 0. And this one, okay, I'm thinking rows times columns. Rows times columns. But I need to change it anyway. So this, the 5 and 7 should be rows. Okay, so that's row 0. And this would be row 1. This is column 0. This is column 1. So it's going from 0 to 1, 0 to 1. Yeah, see, I have to really think hard on that. And then our other one should cause us to go, let's see if that's true here. I'm not going to think about it too hard. I don't think that hard this time of night. Now, variable length arrays. In early versions of C, all arrays had constant size. But what if you don't know an array's size at compilation time? To handle this, you have to use dynamic memory allocation with malloc and related functions. Memory allocation. C standard allows you to handle arrays of unknown size using variable length arrays, VLAs. These are not arrays whose size can change. That would compromise the integrity of nearby locations in memory. Variable length array is an array whose length or size is defined in terms of an expression, evaluated at execution time. They tell you program 6.23 declares and prints several VLAs. Note this feature is not supported in Microsoft Visual C++. Okay, so I got my my function prototypes up here. I'm passing in size, which is an integer, and then I'm passing in this right here. Remember, the brackets indicates us that we're passing in an array. And same here, row and column. Here in my main, I probably gather all the information, do scanfs, read in that, so forth. Here I'm declaring a one-dimension variable length array. Here I'm declaring a multi-dimensional array with my rows and columns. Test size of operator. So we got our size of the array. I don't think I did that in this class. I think it was maybe it was this class. Yeah, it was. I hard-coded that earlier. Remember how I hard-coded that? Because I couldn't remember the exact command. The size of is it allows you to return that. Okay, so looks like it just builds some arrays. Doesn't ask for it. It's kind of tedious when it asks for it. Nothing exciting there. Here's my print one-dimensional array. So I'm bringing that in. And the size is being brought in here, so it's not hard-coded. And then this loops through for our size as our printf and so forth. And again, here we're bringing in rows and columns. We don't have that hard-coded. It's coming in as a parameter. So this can be set up to handle any size array. Notice here, this is referring to row 1, row 2, and array size. I was looking for what was in that. Array size, row 1, row 2. So this is not being hard-coded at all. It's being brought in. So it's loading those in. And then that over here is what's used to define these. So this is your variable length declaration right here. I've never actually used, maybe I have and I just didn't know it, but I've never used a version 99 on this. Okay. Then it prints out the results, asks you how big the one-dimensional array is. It says 6, and then it asks you to, or maybe generates these automatically. Generates those automatically, so 0 to 5. My first two-dimensional array, we say is 2 rows, 5 columns. And you see it created a 2 by 5. Next one is rows by columns, so that's a 4 by 3, so 4 rows and 3 columns. The syntax for passing a VLA as a parameter function, same as with the normal fixed length array, so nothing different there. That's probably about all exciting stuff on that. Programming I've done, I did not have to worry about that because all the machines I was working with had plenty of memory. If I burnt a few extra bytes, who cares? If you're going into engineering, you can't take that kind of approach. You got to think of efficiency. Electrical engineering, I was teaching assembly language earlier tonight, and this time I didn't about fall asleep. It was kind of halfway exciting, really. Maybe I've become assimilated or something. I don't know. But I was programming it, and there was one bit of code that I wasn't sure if that piece of assembly language should be where it's at. I wondered if it should be up above. Normally, I wouldn't matter because efficiency, who cares? But again, when you're programming at a lower level, you need that because sometimes that inefficiency you multiply it times a million times, and it becomes a horrible lag in whatever you're designing. Okay, secure C programming. Bounds checking for array subscripts. It's important to ensure that every subscript you use to access an array element is within the array bounds. That is greater than or equal to 0 and less than the number of array elements. A two-dimensional array's row and column subscripts must be greater than or equal to 0 and less than the number of rows and columns, respectively. Allowing programs to read from or write to array elements outside the bounds of arrays are common security flaws. I would have swore it actually just gives you an error. But I'm probably wrong. Other programming languages it does. C is not that big, so let's see what that gives us. Get rid of all that. Four. That's interesting. We have a 50 in there. I do see why that book focused so much on C. Other programming languages wouldn't let you do that. It gives you an out of bounds error of some sort. 0. Sure enough, you can do whatever you want. Let's see. Reading from out of bounds array elements can cause a program to crash or even appear to execute correctly while using bad data. Writing to an out-of-bounds element known as a buffer overflow can corrupt a program's data and memory, crash a program, and allow attackers to exploit the system and execute their own code. As we stated in the chapter, C provides no automatic bounds checking for arrays, so you must provide your own. For techniques that help you prevent such programs, see the CERT guideline. Those are really exciting. ARR30-C at www.securecoding.cert.org. Scanf_s. Bounds checking is also important in string processing. When reading a string into a character array, scanf does not prevent buffer overflows. The number of characters input is greater than or equal to the array's length. Scanf will write characters, including strings terminating null character /0 beyond the end of the array. This might override other variables' values, and eventually the program might overwrite to string /0 if it writes to those other variables. Functions determine where strings end by looking for their terminating /0, so that's why you don't want to overwrite that. For example, function printf outputs a string by reading characters from the beginning of the string to memory and continuing until that string /0 is encountered. If the /0 is missing, printf might read beyond the end of the string to encounter some other /0 in memory. The C standards optional Annex K provides new, more secure versions of many string processing and input-output functions, including scanf_s, a version of scanf that performs additional checks to ensure it does not write beyond the end of a character string used to store a string. And assuming that my string is a 20-character array, the statement scanf_s reads a string into my string. Function scanf requires 2 arguments for each s in the format string, a character array in which to place input string, and the number of array elements. Okay, so that's the variation on that. Second, these arguments used by scanf_s prevent buffer overflows. I assume it means a 20. For example, it's possible to apply a field width for %s is too long for the underlying character array, or to simply omit the field width entirely. If the number of characters input plus terminating null character is larger than the number of array elements, the %s conversion would fail. Because the preceding statement contains only one conversion specifier, scanf_s would return 0, indicating no conversion was performed, and my string would be unaltered. In general, if your compiler supports functions for the C standards optional Annex K, you should use them. You might have noticed that throughout this book, we never use single argument printfs. Instead, we use one of the following forms. When we need to output a /n after the string, we use a function putS, which automatically outputs a /n. When we need the cursor to remain on the same line as a string, we use function printf as in this. Why don't you use a single argument? Maybe that's next slide. When printf evaluates the format control string in its first and possibly its only argument, the function performs tasks based on the conversion specifier in that string. If the format control string were obtained from the user, an attacker could supply malicious conversion specifiers that would be executed by the formatted output function. I don't think I've ever even asked the user for a format control string. Interesting. Now that you know how to read strings into character arrays, it's important to note you should never use a printf format to control string, a character array that might contain user information, and then they give you more guidelines. Then we're done with that chapter. That's probably a good place for a 10-minute break. So let's go ahead and take a break, and then we'll go into the next chapter. Let's go ahead and start again. This is chapter 7, C pointers. Our objectives, in this chapter you'll learn pointers and pointer operators, to use pointers to pass arguments to functions by reference, the close relationship among pointers, arrays, and strings, and to use pointers to functions, and to define and use arrays of strings. And there's our different sections. In this chapter, we'll discuss one of the most powerful features of the C programming language, the pointer. Pointers enable programs to simulate pass by reference, to pass functions between functions, and to create and manipulate data structures. I.e. data structures can grow and shrink at execution time, such as linked lists, queues, stacks, and trees. Chapter 10 examines the use of pointers with structures. Chapter 12 introduces dynamic memory management techniques and presents examples of creating and using dynamic data structures. When we're passing and just talking about one piece of what was in that introduction, but give you an example. I got this paper right here. Maybe this is an important paper, and I want to give it to you so you can record some information on it. Well, I'm not going to give this to you because it's important information. So what I'm going to do is I'm going to go make a copy of it. I'll give you the copy. You'll make your changes to the copy and then pass it back to me. And then I'll update the original. Now that's one way to do it. That's when they're referring to pass by reference, pass by value. That's where we're making a copy. We're passing by value. Pass by reference. You can almost think of it as I give you the piece of paper and I say, update it directly. You update it directly, you hand it back to me. So there's no copy made and so forth. You're accessing it directly where it sits on that piece of paper. That's the way it is with a pass by reference when you got memory. Instead of making a copy and passing it as a parameter, an argument to your function, you're passing in the memory location. And then your function is going to update that memory location directly. And we've mentioned that before, how that's in terms of arrays, when you do that, that's a performance consideration. Not that you'd have a billion elements in an array. I doubt it'd handle that size. But if you had a huge number of elements in your array, instead of making a copy of that and passing it as a parameter into your function, which would be a lot of overhead, just to really slow your performance down, what we're going to do instead is we're going to say, hey, okay, here's where it's located at in memory. Here's the location of it. And so then through your code, you're going to update that array directly into memory. When you get done running that function, I don't have to reset anything because you already updated it directly in memory. So that's kind of the concept behind, or one of the concepts behind it. I talked, I think, in this class about how you could use pointers to sort. Very powerful. If you go on and take that a data structures class, you got a huge amount of records. Let's say you got 5 million records, and you're trying to insert a new record in there in your database. Well, you could shift all the records down and then put that new one so it'd be in alphabetical order. You could throw it at the end and then do some kind of sort algorithm to resort it. Because when you run your reports, you want it to automatically be sorted. You don't necessarily want it to, and I'm talking very low level here. I know databases handle this for you and everything. But you don't want to sit there and have to sort it each time you're accessing the data. Well, and I couldn't tell you what the popular databases use for this insertion technique, but if you got it sorted already, using pointers, you point to the next number. Then you can use a binary search concept to help figure out, where's it stored at. And based upon that, then you can, let's see, could you use binary search? Yeah, you could use binary search. Based upon that, then you could figure out where you need to insert it at. And again, binary search is very efficient. You can easily locate where it should be at, and then you just reset a few pointers, and you're done. So when they say it's powerful, they're not just blowing smoke. It really is. Okay, pointer variable definitions and initialization. Pointers are variables whose values are memory addresses. Normally, a variable directly contains a specific value. Over here. That's what we're talking about. A variable directly contains a specific value. So we're assigning 3 to num1. A pointer, on the other hand, contains an address of a variable that contains a specific value. In this sense, a variable name directly references a value, and a pointer indirectly references a value. And we'll look at that here in a second. Referencing a value through a pointer is called indirection. Like here we got the name count directly references a variable that contains the value 7. The pointer count pointer indirectly references a variable that contains the value 7. Count pointer doesn't actually contain 7. It contains, again, the memory address where that's located at. Declaring pointers. Pointers, like all variables, must be defined before they can be used. The definition, int, and then asterisk count pointer. You see how you put the asterisk on it. Not that it matters. I'll put it all lowercase like they have. num1. That right there, without the asterisk, would be just a variable. By putting an asterisk on it, then that's a pointer to that. So pointer to an integer. It says counter pointer is a pointer to int. Now the count pointer doesn't have anything to do with the count here. Also, the variable count is defined to be an int, not a pointer to an int. So Two different declarations there. The asterisk applies only to count pointer in the definition. When asterisk is used in this manner in definition, it indicates a variable being defined as a pointer. Pointers can be defined to point to objects of any type. To prevent the ambiguity of declaring pointer and non-pointer variables in the same declaration as shown above, you should always declare only one variable per declaration. So they're saying don't put it on the same line. Put it on separate lines, what I just did here. And again, keep in mind, these two have nothing to do with each other. This is just a regular variable, and this is a pointer to something. Common programming error. The asterisk notation used to declare pointer variables does not dispute to all variable names in the declaration. Each pointer must be declared with the asterisk prefix to the name. So if you wish to declare X pointer and Y pointer as integer pointers, you use int asterisk before each one of them. We prefer to include the letters PTR and pointer variable names to make it clear that these variables are pointers and thus need to be handled appropriately. That's why they put the pointer on the end like that. So it doesn't like my naming. They put pointer on like that. Because later on in the program, when you're not sitting there looking at that asterisk before it, you don't know whether this is an actual variable or a pointer. And so that's what they're talking about. Having a pointer on there is actually good programming practice. Initializing and assigning values to pointers. Pointers should be initialized when they're defined, or they can be assigned a value. A pointer may be initialized null, 0, or an address. A pointer with the value null points to nothing. Null is a symbolic constant defined in the standard def.h header and several other headers, such as standard IO. Notice I got standard IO here. What they're saying is I can set counter equal to all uppercase or lowercase. It says uppercase. We set that equal to null. Let's see if that runs. Yep. Okay. Doesn't do anything, but that's what they're referring to. Now, if I didn't have the standard IO brought in, then I couldn't access that null. What's that mean? Well, it's not pointing any memory right now. Initially, pointer to 0 is equivalent to initializing a pointer to null, but null is preferred. When 0 is assigned, it's first converted to a pointer of the appropriate type. And the value 0 is the only integer value that can be assigned directly to a pointer variable. Error prevention. Initialize pointers to prevent unexpected results. Now we got the ampersand, the AND symbol, or address operator is a unary operator that returns the address of its operand. For example, int y is equal to 5. We got int and then asterisk, y pointer. The statement y pointer is equal to the ampersand y assigns the address of the variable y to the pointer variable y pointer. That's what makes the connection between them. So here, let's say I want to point this counter num1 to this num1 variable here. You put the ampersand before it and say num1. Where have you seen that already? In the scanf, right? Remember how you do a scanf? You do %d like that, and then you do your ampersand, num1. By putting that on there, that's referencing your memory address directly. Okay, assigns the address of the variable y to the pointer variable y pointer. Variable y pointer is then said to point to y. Figure 7.2 shows a schematic representation of memory after the preceding assignment is executed. So we got our original value here, and then we've got a pointer pointing to that in the memory. Now you can print out the value of that. I don't think I remember the format specifier for a pointer. But let's just play a little bit. Printf. I'm pretty sure %d won't give us anything meaningful in terms of the memory address. And, well, let's print num1. I wonder if it's %p. That makes sense. Well, maybe I was wrong. Maybe you can use %d. The 3, it just returns the value num1. Now this should be pointing to the memory address, and I don't know if that's a memory address where that's stored at or not. We're going to see if that's the correct specifier. I don't know why, but it made me think it should be a %p. That actually looks better. That's hex. So that makes me think that that is memory, but we'll see in a second. Okay. Here's y, and they say it's at this memory location. Then y pointer, the value it contains is the pointer to where this is stored at. The unary asterisk operator, commonly referred to as indirection operator or dereferencing operator, returns the value of the object to which its operand, i.e. a pointer, points. For example, the statement %d and you put an asterisk on there, prints the value of the variable. So right here, that's saying if I do a printf %d and I put an asterisk, counter num1. This will no longer print the memory location where it's stored at. It should print the same value as num1 has, which is 3. But let's see. 3, and I think a memory location, and then 3. Using asterisk in this manner is called dereferencing a pointer. Dereferencing a pointer has not been properly initialized, has not been assigned to point to a specific location in memory is an error that could cause a fatal execution time error, or it could accidentally modify important data and allow the program to run to completion with incorrect results. Suppose the minute I start playing around is when I crash my machine, so maybe I better not do it. But they're saying here if I don't initialize it, then I just try to print the result. Demonstrating the ampersand, the and symbol, and the asterisk operators. Figure 7.4 demonstrates pointer operators, ampersand and asterisk. Printf conversion specifier %p. Yeah, it is %p. Outputs a memory location as a hexadecimal integer on most platforms. See Appendix C if you don't know hex numbers. Notice that the address of A and the value of A pointer are identical in the output, thus confirming that the address of A is indeed assigned to the pointer variable A pointer. And the ampersand and asterisk operators are complements one another when they're both applied consecutively to A pointer in either order. That's interesting. I don't think I've ever seen that. one gives you the pointer reference, and the one gives you the value at that pointer reference. So that's what they mean to undo each other. I just didn't know you could put them next to each other. Okay, so here we got a variable a equals 7, and I got a pointer, a pointer, and then I point a pointer to a. I can print out the address by doing the %p, and you can do the value of a pointer. When? So printf address of num1 is %p/n, and they're putting an ampersand besides num1. So that's going to access that. Printf the address of num1 pointer, I won't write all that out, is %p/n. And here they're just wanting the regular value, right? Yeah. I don't know why I made that so long. Okay, so there's printing the memory address of num1, and then it's printing the value of num pointer, which is the memory address. The value of A is %d, the value of, and then they got the asterisk here, so let's take a look at that. The value of num1 is %d, num1. And then the other one they want is put an asterisk before the pointer. What in the world is that? The value again. Okay, the value of asterisk our pointer is %d, and then put the asterisk before our pointer. Three and 3. So they're just indicating you that whether you're working with the pointer or the actual variable, you can access, at least in this case, the same information. Here's where you can put them next to each other. The ampersand, asterisk, asterisk, ampersand undoes each other. So complements. And both those return the memory address. Grab a drink. Somewhere on here you'll see these symbols we just looked at. The ampersand and the asterisk. There's the ampersand. Okay, here's the asterisk down here. This is the multiplication. I was looking for 2 asterisks. And then this asterisk up here relates to our memory that we've just been looking at. So those pointer operations are done before multiplication, division, addition, subtraction, and all that. Now, passing arguments to functions by reference. 2 ways to pass arguments to a function. You pass by value. And we've already seen that. INT, double it. And I'll pass in INT num1. And down here, int double it. I'm passing in num1. Now return 2 times num1. Okay, so then I can say num1 is equal to double it, num1. So I'm going to pass in num1 in as our parameter, our argument. It's going to calculate it, return the value, then I'll assign it back to num1. So that's by value. And then I'll print out the value. Let's see, num1 equals %d/n num1. So let me run that. Return 6. Nothing too exciting, just doubled 6. Okay. All arguments C are passed by value. Many functions require the capability to modify variables in the caller or to pass a pointer to a large data object to avoid overhead of passing the object by value, which incurs the time and memory overheads of making a copy of the object. In C, use pointers and indirection operator to simulate pass by reference. When calling a function with arguments that should be modified, the addresses of the arguments are passed. This is normally accomplished by applying the address operator, the ampersand, to the variable in the caller whose value will be modified. As we saw in Chapter 6, arrays are not passed using the operator ampersand because C automatically passes the starting location and memory of the array. So it's by default passing in the memory location. When the address of the variable is passed to a function, the indirection operator or asterisk may be used in the function to modify the value at that location in the caller's memory. This just talks about the program. Here's a pass by value, just like what I created. Cube by value. Oh, it's returning n times n times n. And then you assigning it back to the number. So this is like we got, again, a copy. I've made a copy in a piece of paper. I'm giving it to you. You're modifying it, passing it back to me, and then I'm updating the original. And that shows you it works. Now, by reference, though, so we got void, cube by reference, and int. And I don't have to return anything because it's updating the memory directly. That's why it's a void. So over here, I don't have to do an int because I'm not returning anything. Double it by reference, int, and what is it, ampersand, asterisk, num1 pointer. And then down here, I got void doBit, double it by reference, and down here, I think it's the same definition. I put an asterisk before it, Check num1 pointer. And now, when I'm updating it, you see I'm using these asterisks here. It gets kind of confusing because you have asterisks for multiplication, you have asterisks for the pointer. The asterisks that are right before the end pointer are your ones for the pointer reference, and the other ones are your multiplication. Yeah, it's confusing. So if I said asterisk num1 pointer, that's going to equal to 2 times, and I'm going to put this in parentheses, num1 pointer. That's this asterisk asterisk you see here. This first asterisk on the right-hand side of the equals, that's our multiplication. And this is what's working with the pointer. Now you notice they don't have anything else. They just had that one line and that's it. Here's where they're calling it. They do a cube by reference and they're doing an ampersand before it. Now I have to look at this myself. When we're doing this, I get them mixed up. Put an asterisk or put an ampersand. I can play with it and find it out, but it's usually easier to do that. So if I call doublet by reference, and I'll pass in an ampersand in num1. And then I'll do another printf, num1 equals %d/n, num1. Let's see if that gives us an error of what it does exactly. 6 and 12. Both of these are updating the value of num1. This one is passing in the old value of num1 as a parameter, as an argument, into my function. It's again, it's creating a copy of it. This is bringing it in. It's assigning memory to it. It's doing the calculation. It's returning it, and returning it as an integer, which then gets assigned back to num1. So I've just updated the original num1. In the process, I've had to use memory locations. The pointer, on the other hand, when I call this function, well, I'm passing in a pointer to where it's stored at in memory. So this is where num1 is stored at in memory. This down here, when I do an asterisk in front of it, that's updating the value in memory. So that when this gets done running, it's going to have it updated in memory itself. And so I don't need to return anything. That's why this is a void, because it's updating it directly. Is there any questions on the difference between those two? Pointers are a little weird to begin with if you've never seen them before. Passing arguments to function by reference. A function receiving an address as an argument must define a pointer parameter to receive the address. That's what we're talking about with the asterisk here. The header specifies that cube by reference receives the address of an integer variable as an argument. Stores the address locally in nPointer. Stores it locally there. And does not return a value. Function prototype for cube by reference, line 6 contains int, an asterisk in parentheses. Names included for documentation purposes are ignored by the C compiler. For a function that expects a single subscripted array as an argument, the function's prototype and header can use the pointer notation shown in the parameter list of function cube by reference. Compiler does not differentiate between a function that receives a pointer and one that receives a single subscripted array. This, of course, means that the function must know when it's receiving an array or simply a single variable for which it's to perform pass by reference. When the compiler encounters a function parameter for a single subscripted array, the form int b with the brackets, the compiler converts the parameter to the pointer notation int asterisk b. Remember, when it's passing an array and it's working with pointers, we're just pointing the memory location, and that's what they're talking about. We have to be careful about that. Are you passing a memory location for a single variable or array or what? Use pass by value to pass arguments to a function unless the caller explicitly required the call function to modify the value of the argument variable in the caller's environment. This prevents accidental modification of the caller's argument. Is another example of the principle of least privilege. I can't really think of too many circumstances where you would work with pointers in this manner here. Amount of overhead that it would save is very minimal when you're talking about one variable. If you're talking about an array of 10,000, definitely you can see a performance, and that's what they're indicating. Even though we show an example with one variable just to demonstrate the concept, this really works better if you're talking about data structures, arrays, and other objects. And this gives you an example of a typical pass by value. Right here, we're declaring number set equal to 5. So we got a memory location, number is 5. We're calling cube by value, passing in number. Here's my cube by value over here. I'm bringing in a number. By default, it has its own memory location, and it's returning n times n times n, and then brings that back over to here and reassigns it to my number. So after the cube value receives a call, we got number 5 here. After cube by value receives the call, it hasn't finished the call. Okay. So number is still equal to 5. And at this point, n has been set equal to 5 because it's done this initial one. Then the next one, okay, number is still equal to 5. It calculates this, n times n times n. And it's equal to 125. It's still not assigned anywhere. We're going to need to return it. Back to here, it returns that value. And so this right here is now equal to 125. N here is back to undefined since we're done with that function. And probably the next step is going to be to set it equal to number, so you'll see this memory location change here. And it does, changes to 125. So that's our typical pass by value. Now a pass by reference with a pointer. The main program, we declare a variable called number set equal to 5. So we've got a memory location of 5. Here's our function we've set up. To begin with, it's your end pointer is undefined. We haven't even called it. Okay, we just called it. So I'm passing in. You see here, I'm passing in the ampersand number. The call establishes this pointer. So it's taking this pointer we have here, and it's pointing to it where it's located at in memory. So it's not passing a value. It's just passing in where is it at in memory. And so now this has made that link. Then it's taking it's pointing to that in memory, which is 5. I'm working with the right side of this now. And so it's got 5 times 5 times 5, which is 125. And it's writing it back out to the memory. So it's not doing anything local here. The pointer is causing it to update the original memory location. So again, a little bit less overhead on that. But it's typically you don't do that with a single variable. Okay, although on unless they got some, usually some of the problems on pointers are just hideous. And I'm not going to torture you in that regard. So usually I make a real simple example. And I haven't used Ditel's book on C for a while, so I have to go and double check. But typically I make up my own example of that, just a real basic one, updating, doubling it, adding 5 to it, something trivial. Okay, the constant qualifier enables you to inform the compiler that the value of a particular variable should not be modified. Constant qualifier can be used to enforce the principle of least privilege in software design. This can reduce debugging time and improper side effects, making a program easier to modify and maintain. If you don't know what you're doing and you're updating memory directly, you're getting a little bit closer to the hardware level yourself, where the pass by value kind of puts a layer in between, where the C programming package, when it creates the compiled version and so forth, it handles that for you, so you don't have to worry about it. Using the constant qualifier with pointers, over the years, a large base of legacy code was written in earlier versions of C that did not use the constant because it was not available. For this reason, there are significant opportunities for improvement by re-engineering old C code. 6 possibilities exist for using or not using constant with function parameters. 2 with pass by value parameter passing, and 4 with pass by reference parameter passing. How do you choose one of the 6 possibilities? Let the principle of least privilege be your guide. Always award a function enough access to the data and its parameters to accomplish a specified task, but absolutely no more. Chapter 5, we explained that all function calls in C are passed by value. A copy of the argument in the function call is made and passed to the function. If the copy is not modified in the function, the original value in the caller does not change. In many cases, the value passed to a function is modified so the function can accomplish its task. However, in some instances, the value should not be altered in the called function, even though it manipulates only a copy. Should not be altered. Can't think of an example of that, but I'm sure they'll probably give us one. Consider a function takes a single subscripted array and its size as argument and prints the array. Oh, I bet they're talking about Okay, such a function should loop through the array and output each array element individually. Size of the array is used in the function body to determine the high subscript of the array, so loop can terminate when the printing is completed. So if I got 5 elements in my array, it goes from 0 to 4. So that's what I'm talking about, the high subscript. Neither the size of the array nor its content should change in the function body. Okay, because we're just going through and printing we're just printing the values. So, okay, I see what they mean now. If a variable does not or should not change in the body of a function to which is passed, the variable should be declared constant to ensure that it's not accidentally modified. If an attempt is made to modify a value that's declared constant, the compiler catches it and issues either a warning or an error depending on the particular compiler. And I really want to get to the example. Okay, that's a non-constant. Non-constant. This is what they're talking about, where you have the constant in front of it. And again, this is in our function prototype. And that tells us that we're going to print. We're not going to actually change anything. And you might say, well, I thought you were the programmer. How could you change anything unless you deliberately change it? Well, yeah, that's true. But some people do strange things. And by declaring that as constant, if somebody modifies the code later on, or even if you forget and think, okay, well, I'll just change it right here, and you're changing it into print characters. Who in the world would think that you would modify the original array and print characters? All you're doing is printing. So those are two examples where it's kind of a catch. So you don't do something by accident. I see that in programming every now and then, where they have a check like that, and your first thought is, well, I had no intention of doing that, and these little tricks here, little programming add-ins that they've done help prevent that. Common programming error. Being unaware that a function is expecting pointers as arguments for pass by reference and passing arguments by value. Some compilers take the value assuming they're pointers and dereference the value as pointers. At runtime, memory access violations or segmentation faults are often generated. Other compilers catch a mismatch in types between arguments and parameters and generate error messages. It'd be nice if they were all consistent. So you look at one particular compiler versus another compiler. Some are pretty good about anticipating your things you shouldn't be doing and either giving you a warning or an error. And some just let you do whatever you want. I doubt if I could write a C program in Visual Studio real fast because you have to have certain parameters at the top. Not saying Visual Studio is a good compiler, although I do like Visual Studio. Let's see if I can even come close. Let's see, file, new, project. Empty project. Windows console application. I bet I could. Let's try that. I bet it's not going to work. I bet it's going to want us to do a console.writeline, which is a Visual Studio add-in. What? Visual Studio 2019. Yeah, that doesn't look promising. Looks like it goes ahead and puts it in the C++ format. Let me do one more, and then I'll give that up. Okay, empty project. View, Solution Explorer. Right click on that and choose add new item, I think. Installed. I don't see C. Oh well. what I was wanting to point out is I'll show you a compiler that checks for issues. Gives you warnings instead of just lets you do whatever. Let's see. There are 4 ways to pass a pointer to a function: non-constant pointer to non-constant data, a constant pointer to non-constant data, a non-constant pointer to constant data, and a constant pointer to constant data. Each of the 4 combinations provides different access privileges, and these are discussed in the next several examples. It might not be a bad place to stop. So I like to leave the last part for any programming questions you have. If you're having trouble with any programs. So we can stop the recording.